All right. Hello, everyone. Welcome back to Advanced Workshop for ACM AI. This week, we are going to be talking about PyTorch. Very exciting stuff. So with all of the theoretical tools that we've been talking about for the past few weeks, now we're kind of going to teach some tools that are going to um, make it so you guys can actually, you know, build models and implement cool neural networks based on what you've learned. So yeah, and hopefully as we go through this PyTorch workshop, we'll do our best to kind of explain like in each step like how this function is related to the theoretical concept, just so we all know what's going on. So yeah, uh, Justin just put the Conda doc in the chat for you guys again. So like yeah, there's a few things to say about this workshop because it's a bit different. So we want you guys to hopefully have your Conda environment open, um, or have the Jupyter notebook open, and then kind of like type the code blocks with us, so you guys can start to develop some intuition and like understand the code. We think it's a lot better if you guys are actually doing it. So um, before we start, like, can I get like yes or no's in the chat? Like, do you guys like have the Conda thing set up? Yeah. Okay, cool. So it looks like at least 5 of you have it. Now if you don't, um, I guess that's okay. Um, we wish you did, but if you didn't, um, so the full code for like everything we're gonna talk about, it's actually like this. There's a link for it right here, and this is in a collab, so it's like all here, so you can see it if you want to see the whole picture. I actually recommend that like you have this open on the side with the slides, because then like if we happen to like go to the next slide and you can no longer see the code block, you can just refer to this and you'll see the code block. So yeah, you should open this as well as the slides. So yeah.
You want to also show how to make a copy if you want to make some changes to it?
What do you mean? Make a
Oh,
copy
yeah,
of
the
this.
notebook. Yeah,
Well,
because
okay.
I don't think you can modify it. Like, it's not everyone can modify it right now.
Um, yeah.
Yeah, so
Well,
you only.
instead of making a copy of this, um, like we're assuming you guys have like the Conda thing set up. So
Mhm.
hopefully you should be doing the work in the Jupyter notebook instead of the collab. The collab's just there for you to reference. So if you want to like see how stuff's different, like you can paste the block into your Jupyter notebook and then make some adjustments or play around with it. And we encourage you to do so. So yeah, before we start the workshop, let me talk a little bit about Conda and Jupyter notebooks, because yeah, I know most of you guys read that doc when you're setting it up, so hopefully the idea behind it, some of the stuff makes sense, but I'm going to talk about it in person as well. So yeah, so let's say you're in your terminal, right? So the idea behind like Conda environments and like environments in general when you're developing anything, not just in data science or machine learning, is that you want to isolate packages um, between different projects. So you might have one project that needs certain packages. Um, like you might need, like in this project, like you need PyTorch, you need um, a lot of packages, right? But in another project, you might not need PyTorch. So what you could do naively is you could just install all of these packages at the user level. So then you'll have all those packages installed on your machine all the time. But that's bad for a few reasons. For one, your package dependencies get really confusing if you install everything at the user level. And usually the idea behind package managers like Conda is that they their job is to like help you manage package dependencies for you. So if you have to install, when you do like Conda install PyTorch, it doesn't just install PyTorch. It installs PyTorch and then like a bunch of dependencies for PyTorch as well. Now, if you had to install all of those by hand, that would not be a fun time, right? So Conda is great for that, and it helps manage the dependencies, and it does a pretty good job. But if you have everything installed at the user level, everything just gets really confusing. And a lot of times, like even Conda will get confused and your package dependencies will get messed up. That's one problem. Another problem is uh, it's very important in software development and in general that like your code is like portable. So when you do a project, like you want to make sure like someone else can like set up your project on their machine. So like otherwise like what have you really done, right? If you spent like a year like developing this awesome video game and you have no way to package it and send it off, then like cool, that's cool that you did that, but like no, you can't really share it with other people. So it's really important that you isolate the packages that are like required for this specific project, so then when you're done you can you can kind of package everything together, and then people who want to start or people want to like build your project or whatever on their machine know exactly what things they need to have installed. So that's kind of the idea behind like using a package manager like Conda. Another really popular package manager is the pip package manager. Um, so I'm sure you guys have like used pip before, like pip install, blah blah blah. Conda is kind of that same idea. It's just Conda. There's a few reasons why Conda is better that I'm not gonna get into, but a lot of data scientists use Conda, so we're using Conda. So if you have your terminal open, right? So you guys should already know how to do this if you read the documentation for the Conda stuff. But yeah, so you should type like Conda activate, oh, Conda activate, and then like the name of your Conda environment. So mine is called PyTorch. Yeah, and then now you'll see there's little parentheses PyTorch uh, on my PS1 thing here. So that indicates that I'm in the PyTorch environment that I created. And then you can do conda list and you can see all the packages that are inside of this environment, right? So there's you guys should also like have a lot of packages here. So yeah, and now that we're in our environment, because we have Jupyter notebooks installed and Jupyter Lab installed, so you should be able to type Jupyter Lab, and then it'll open Jupyter Lab at your current directory. Um, So, or I think it's actually the last directory that it was opened in. So for me, it was opened in the PyTorch directory. But yeah, so it'll open it in this directory. So this uh kind of has your file system, right? It's you can see it's like the same organization of your file system that's like in your computer. So like I have like I can like ls into hold up. Yeah, so I can like if I do ll PyTorch, like you can see like all these things. Like I actually have a folder called PyTorch um, on my computer, and then it actually has all of these kind of files in it, right? And you can clearly see that they're all here, right? So um, yeah, so that's nice. So then how does this work? Like what does this actually do? Well, when you type Jupyter Lab, it opens a port. Um, so like here it opens the 8888 port and starts a server. So then you can basically you're running a server that kind of emulates I don't know if emulates the right words, but it kind of replicates your file system here in a manner such that you can actually work with these IPy notebook files, right? So this is the notebook file that we're going to be looking at today. So this is where all of the kind of code blocks on the slides are from. Now, the idea of like code blocks, like this code block mentality, is and this is the same way that the Colab works, right? You can see it's like the exact same idea. You have like blocks of code, right? It's the same idea. So the idea is this is really useful for prototyping things. And machine learning engineers, I've talked to like a lot of machine learning engineers who like actually like have jobs in industry, like people who work at Tesla and stuff like that, and they say they use Jupyter notebooks for a lot of their stuff, because when you're first prototyping a lot of machine learning models and whatnot, it's really helpful to be able to basically isolate your code into a bunch of little blocks and then run those blocks independently of each other. They're not, and by independently I mean you can like run one block without having to rerun all of the blocks, right? So you could just put all of these blocks like in the order that they're presented, like in a Python file, and then you could run it, and then it would do the same thing as if you just ran this block, this block, this block, this block, this block, this block, etc. Right? But like this is really useful because if you have to make a small change in one of these blocks, you can just make that change and then rerun that specific block without having to rerun the entire file. Because if you have to rerun the entire file, it takes a really long time, especially because a lot of times, like as we'll discuss later in the workshop, some of your blocks are going to have like training loops in them. Like here, you're going to have a training loop in it. So then if you have to run the whole, like let's say you have to change something somewhere else, and if you had to rerun the entire training loop just to see that you change something over there, it's really inefficient because the training loop takes a really long time to run. So it's really useful to be able to isolate your code like this. And then once you like figured out exactly how your model is going to work, once you finished it, then a lot of times people export it to just a normal Python file for use. But for prototyping, this is really useful. So it's really important to understand how these code blocks work. So like, yeah, so if you run, so you can press like this little play button and it'll like run the code block that you have selected, right? So that just ran this code block that imports all these things. But if I go ahead and where's the restart button? One of these, I think it's this, yeah. So if I restart the kernel real quick, so if I try to run this code block, it's gonna get mad because I had to run this code block first, right? Because you only ran this code, and this code uses a function from the Torch library, but I didn't import Torch yet, right? Because I only ran this block. So you have to make sure that like you run this block before this block because this block depends on this block. Okay, does that make sense? It's pretty intuitive idea. If you only run this block without running this block before it, well, you haven't run this code yet, so you haven't imported Torch yet, so it's not going to work, right? Whereas if I was to now run this code block and then run this code block again, we're okay because now I have Torch imported, right? So that's kind of the idea behind these code blocks. So hopefully, so you guys all have like your Jupyter notebook open, kind of like I have open. And then with that, we can actually get started on the workshop. So I'm going to hand it over to Ben.
Thanks for that introduction. Hopefully, if you guys have any questions, you can ask as well whenever you want. We prefer you unmute, but if you have questions and you don't want to talk out loud or you can't, then you can also ask in the chat. Right. So now, let me know if you guys can see my screen. Let me open up there. Okay, awesome. Thanks. Make sure I have the chat open so I can see. All right. So first, today what we're going to do is we're just going to go over the basics of PyTorch. So we're going to start off with an introduction to tensors in PyTorch. Then we'll talk about loading data for training and testing. Then we'll talk about how to construct a model in PyTorch, and finally how to train and test that model. The top right corner, we have the same imports. It's similar to what you saw in the notebook that Paymon just showed you, but if you haven't already entered these lines in your either Jupyter notebook or Python file, you should add them now because we'll be using these imports throughout the rest of this workshop. So we just want to get it out of the way for now. Right. I'm just going to move on. If you missed any of like those lines on the slides, then you can have the Google Colab notebook open on the side, like Paymon suggested earlier, or you can have the slides open as well. So I'm not gonna like wait on the slides for you guys to copy them over, since it's probably easier to copy from the notebook anyway. But first off, we want to talk about tensors. Torch tensors are really the same idea as like arrays in any other language. From a mathematical perspective, what they are is like a generalization of like vectors and matrices, right? So you can think about it like a zero tensor is like a scalar, right? There's no dimensions to it. A one tensor would be like a vector where there's a single dimension. A two tensor would be like a matrix where there's two dimensions, and a 3, 4, and n vector or n tensor would just be however many dimensions you add onto it. From a computer science perspective, you can think of this just like as a nested array. Like in Python, you can nest lists, and you can use that as a representation of like a matrix or a vector, and so on and so forth. They're also very similar, and actually, I think, modeled off of the same arrays as NumPy. And you'll actually see a lot of commonalities there, like a lot of the same things you can do with NumPy arrays, you can do with PyTorch arrays as well. But there's also some more extra tools that they add, some quality of life improvements and also efficiency improvements with PyTorch tensors. You can do things like auto differentiation, which we'll go into, which is also more specific for machine learning. And you can also do things like run it on the GPU. Like I believe NumPy only runs on the CPU. So if you have like very large tensors, then it wouldn't be as performant to run it in NumPy as it would be in PyTorch.
Yeah, so to add to that, so like
Mhm.
yeah, so if you guys have used NumPy, like torch tensors are like they're literally like NumPy arrays. The only difference, I mean, there's other subtle differences, but the only difference is that we care about is that they auto track like the gradient path. So that's basically good because it can do backprop for us, which is like very, very nice. And then like Ben said, you can run it on the CPU or GPU. Now, GPUs are GPUs are like a lot faster at computing matrix operations than CPUs are. So the idea is you can allocate your torch tensor to the GPU's VRAM instead of the CPU's instead of onto the CPU, and then the GPU will perform the computation instead of the CPU, which means it'll basically work a lot faster. And then we're not actually going to talk about like allocating. I don't think we talk about allocating tensors to the GPU here, but just know that you can do that. So yeah.
Yeah, we'll share the documentation later, and there's some great guides on how to do a lot of the things that we don't mention in this workshop. But we're just going to stick with the basics, just enough for you guys to kind of get started with the project next week. So yeah, thanks for that. And I think we can move on to the next slide. I want to first talk about how to initialize tensors. You can actually initialize them because they're very similar to lists and NumPy arrays. You can initialize them with lists. So in this line, we have, let me see my cursor, there it is. We're creating a new tensor, and we're creating it off of a nested Python list. This list has 2 dimensions. You can see there's an inner array or an inner list with 5.2, 2.3, and then the second row is 4.3 and 4. Oh yeah, one thing to note about this is that you got to be careful. It's only a single argument here where we're passing it a single list where it's like a list of lists. So it's only a single list that's given as an argument, even though it's composed of more than one list within it. You can also have more dimensions as well. And if you had like a 3-dimensional list, then you could have another list kind of nested in here as well, like in place of the 5.2. You can play around with this, and you can try to convert different lists and arrays to PyTorch tensors. You might find that some of them don't work, like if you're missing, or like if the dimensions don't match, then you can't really create a tensor out of it. But this is the simplest way, again, to initialize a tensor in PyTorch. Also, a note on about the types. PyTorch will automatically infer the data type from what you provided. In this case, we're giving it floating point values. So I believe by default, it infers this as like a single precision floating point number. It isn't shown here like it is in NumPy sometimes, but you can also add an argument if you want to be explicit about what data type you're using. Like if you want to make sure that this is a double precision, like 64-bit floating point number, you can also specify that. There's more details in the documentation and more options, but we're not going to go over them because they're not relevant today. Another thing you can do with initialization is actually initialize a array with all zeros, all ones, or random numbers. By random, it's just going to be a number between 0 and 1. I believe 1 is not included, but 0 is included. And so it's these are just convenient for example, when you're initializing the weights, you kind of want to like initialize them random. You can initialize random weights using torch.ran. You can also initialize arrays that are zeros or ones using this. The arguments are actually a little different because instead of specifying the exact values for each of the elements, what we're doing is we're specifying the dimensions of the tensor. So in this case, we're giving it a list with 5, 2, and 3. And instead of specifying the values that go into the tensor, what we're doing is we're specifying the dimensions. The first dimension is the outermost one, right? So if we represent this as like a nested array, then the outermost is this first number, and the innermost one is this third number. So you can see there's 1, 2, 3, 4, 5 nested arrays in the outermost array. And then there's 2 within each of these groups. And then there's 3 in the innermost, right? This is not necessary. When you're passing it in as an argument, you want to give it as a list, again, to make it a single argument. But I believe it's also possible to remove these brackets. I wouldn't recommend you do that, especially when you have extra arguments past this, like we'll show later, like keyword arguments. It's not going to interfere with it, but it's just more clear if you bundle it together as a single argument using brackets to make it a list. Or you can even use parentheses to make it a tuple as well.
Yeah, so do you guys understand, like, this slide's really important, not just because it's like, look, you can do things to all zeros or all ones, but it's really important for understanding how dimensions are labeled in PyTorch. They're labeled from outermost to innermost, right? So you can always think of the dimension on the far right as like how many entries are in like the innermost cell. So that you can see in each innermost like cell / list, it's like there's 3 entries. And then one level up, well, in that, then there's two of those sets of innermost lists in one of these more outermost lists, and then there's 5 of those. So I hope you guys can kind of see how it goes. Like outermost is the left one, and then innermost is the right one. This is not the same as some other. I think TensorFlow is the other way. For example, I think TensorFlow is innermost to outermost. I'm not 100% sure, but I think so. So it's important that you guys understand how the dimensions work. So if you guys understand that, can you say like yes or no in chat?
Awesome. Yeah,
Okay, cool.
this is useful because these are not the only methods or functions that are going to take in dimension parameters like this. That's why you're going to see this again and not in different contexts.
Yeah,
So it's important to understand it.
Yeah, it's gonna show up. Like if you don't know how the dimensions work, you're gonna have a bad time. So it's really important that like it shows up everywhere.
Yeah, you don't
And
want to
like
be guessing with them.
yeah, you're gonna get like an error somewhere. Like I guarantee you, like if you're like doing a project and you're like trying to train some model, you're gonna get some error about like, oh, this tensor dimension does not match this one when you're doing like some operation somewhere, like when you're multiplying something or something. And if you don't know how the dimensions work, you're gonna have a really hard time like debugging it. So it's really important just to always like have a really strong emphasis on understanding the dimensions here.
Okay. Yeah, that's pretty much sums it up. I think we're going to move on to the next slide. Now we're going to talk about manipulating the dimensions. Again, this is why we want to understand the order. We want to make sure that you understand them because, like, when you're manipulating the dimensions, you're gonna you're gonna change the dimensions. You have to understand what you're changing and what you're gonna get as output. So one function you can use to reshape a tensor is torch.reshape. And what this will do is it will take in as input, the first argument is the tensor that you're going to reshape. And then the second argument is going to be a collection, so either a list or a tuple specifying those dimensions. This is the same idea as the previous slide where we're specifying the dimensions for like a tensor of all ones or all zeros. But in this case, we're reshaping an existing tensor. So in this example, what we're doing is we're starting with a tensor that's 5, 3, 2, 7. So this is like a matrix, right? And you can also print out the size of that tensor using the tensor.size. And it will tell you that the tensor is 2 by 2. So again, this is in the same order. There's 2 rows or 2 of the outermost or of the outer array. There's like 2 entries in the outer array. That's what I'm trying to say. And then the second 2 means there are 2 entries in the inner array. And then what we're doing here is we're reshaping that array to a new dimension of 1 by 4. So now we have 1 entry in the outermost array and then 4 entries in the innermost array. or I'm interchanging array and tensor because I'm a little bit used to NumPy, but they're the same idea. Whenever if you ever catch me saying array, I mean tensor, by the way. And then again, it gives you the size back, which is exactly what you gave it, 1/4. Squeeze is another useful one. So squeeze is a little bit unusual, or it's not as intuitive as like something like reshape. Squeeze, what would it do is for any dimension that's of size 1, it's going to remove that because it doesn't actually contribute anything. Like, well, it does. It just change the shape of it, but it doesn't change the data that it contains. So when we squeeze a array, in this case, or a tensor, I need to catch myself. If we squeeze this tensor, we notice that there is one dimension. The first dimension is of size 1. So when we squeeze it, we remove that dimension. And if you notice what happens to the tensor, before it was like a single row or a single element in the outermost column or outermost array, and then there are 4 elements in the innermost tensor. Now there's only the outermost tensor and there are 4 elements in it. That's how it removed that dimension. It's not necessarily the first one. Like you can have a single dimension, like it could be 1, 4, 1, 1, 1, 1, and it will still remove. And when you do squeeze, it's going to remove it and shrink it down to just a single dimension.
Yeah, so
Size
one
4.
way you can think of it is I think of it like buckets inside of more buckets, right? So let's start at the top when you have a 2x2 tensor. So you have one big bucket, and then you have 2 small buckets in that big bucket, and then in each of the 2 small buckets you have 2 entries. Okay? So that's how you have it. And then when you do the reshape to a 1x4, so now you have one big bucket and one smaller bucket in the big bucket. So before there were 2 small buckets in the big bucket. Now there's only one small bucket in the big bucket. And now all 4 of the entries are in that one bucket. So basically it's like removing one of the small buckets and then just taking the things that was in one of the small buckets and putting it in the other small bucket. So now there's only one small bucket. And then when you squeeze it, basically you just get rid of the really big bucket on the outside now. So now you just have one bucket and has 4 things in it. So with the 1x4, you had one big bucket with another smaller bucket in it that has 4 things in it. And then when you squeeze, now you just have one bucket with 4 things in it. So I don't know if I just thought of that bucket analogy. I don't know if that helped at all, but because
Hopefully it helped.
yeah, like I remember this was like pretty confusing for me when I was first learning it, but yeah, because you guys can see how in the 4x1 tensor on the right, yeah, so Ben's pointing to it, like there's one list inside of like another bigger list, right? So you're kind of just chopping off that outer list when you do the squeeze. And this is actually really important here. So maybe a question that some of you are thinking in your head right now is, well, when I reshaped it, instead of reshaping it to a 1x4, why didn't I just reshape it to like 4? Wouldn't that just achieve the end result where we just have one bucket and then all 4 things in the one bucket? Well, this actually would give you a runtime error, because for the reshaping operation to work, basically the number of dimensions that you have needs to be the same. So in both cases. So for example, 2x2 was what we started out with. So there were 2 inputs for the dimension. There's a 2 and then there's another 2. And then when you reshape it, you have a 1 and a 4. So it's still 2 different values. 1 and 4 are 2 different values. 2 and 2 are 2 values, right? So they both have to be 2 values. You can't reshape something that's 2x2 into 4, because there's only one entry when you say 4, but there's 2 entries when you say 2. So, but if you want to do what you would think would happen when you reshape it to 4, you can just squeeze the result you get at the end. So when you want to do something like this and you want to basically flatten everything down into one array, what you'll probably do is you'll reshape things such that all the other dimensions are 1, and then the dimension that you actually care about is like the biggest value, and then you'll just squeeze all the other dimensions up. So this is actually something pretty common that happens when you're reshaping tensors.
Yeah, thanks for that.
if you're reshaping a tensor like for A, because you reshape it like a 1 by 5, or is it only like if the new thing that you shape it to has to have like the same number of elements?
Yeah, I don't think that would work because you would run out of numbers. So I don't think it would work.
Yeah, I believe it has to match like the number. Like if you multiply 1 times 4, you get 4 numbers.
Yeah, so
So
someone said, yeah. So if you did one
yeah.
by 5, I don't think it works. If you do 1 by 3, like someone asked in the chat, it still doesn't work.
Mhm.
Like it has to it has to work. Like it has to mathematically make sense. You have to be able to do it mathematically. Otherwise, it will give you a runtime error. And usually Python's pretty descriptive. It'll be like, yeah, look, your dimension's off. But if you don't know like where it's off, like like I said, you're gonna have a bad time. So yeah.
Right.
We
Yeah,
can
so
move on from this.
you guys can play it around with in Conda or the notebook if you're curious or you
Yeah,
want to try it out.
hopefully you guys like are writing these code blocks like, and then you can like literally test this on your own. Like you can just
Oops.
try it.
Whoa, what did I just do? Hold on.
You went forward one extra slide.
Yeah, some other windows closed. Oh, okay, I'm back. All right. Yeah, sorry I interrupted you. Let me go back.
No, you're good.
Okay. Yeah, so hopefully you guys are testing it out and we can move on to the next slide, which is going over operations. In this slide, we're only talking about element-wise operations. If you add tensors using like the plus sign symbol, this is going to do element-wise addition. And when you're multiplying it, it's also going to do element-wise multiplication. It's not going to do a dot product and it's not going to do matrix multiplication. It's going to do element-wise multiplication instead. So if we look at this first one, we have 2 tensors, and this is a 3 by 2 tensor. So we have like, you can think of it like a matrix with 3 rows and 2 columns, and it's going to be like 2, 3, 1, like that. And when we add them together, the result is 2 plus 3 equals 5, 7 plus 7 equals 14, and then you can kind of go down, and you can see it adds each of the elements together, and our result is going to be a tensor with the same dimensions because we're adding them element-wise. This is also like in the previous one, we talked about how squeezing was important for operations like dot products. It's also important for operations like this, where the dimensions have to match. Like if this was a 3 by 1 and this was a 1 by 3, you wouldn't really be able to add them because the dimensions don't match, even though like if you look at the 2 arrays, they would match. So if you squeezed both of them, then you would have 2 tensors with a size 3, and then you would be able to add them together like this. So whenever you're doing adding or multiplying element-wise, the dimensions of the tensor have to match.
Yeah, like it also wouldn't work if like the top one was like 3, 2, 3, 2, 1, and then the second one was 3, 2 for the same reason, right? Like they have to exactly match. So if the top one was like 3, 2, 1, you would first squeeze the top one. So then it would now be a 3 by 2, and then you could add them.
Yep. And then another operation, this is probably what you're more familiar with, is like a matrix multiplication. If you want to do a matrix product, then you do torch.matmul. And this does what you'd expect if you've taken linear algebra or have worked with matrices before. Where we have this tensor, our dimensions are 3 by 2, and then the other tensor is a dimension of 2 by 5. And again, just like with matrix multiplication, these 2 dimensions have to match. And our resulting dimensions are going to be 3 by 5 because these are the 2 dimensions here. I won't go over the multiplication because I hope you guys are able to do it yourself. One thing to note here is that if you have tensors that are, if you have like a tensor that is like a 1 by something, then it would just be like a vector multiplied by a matrix. But if you had higher than 2 dimensions, so for example, if this was like 3 by 2 by 3, and then and 2 by 5 by something, then you have to be a little bit more careful because what it's going to try to do is like batch matrix multiplication. So it's going to treat it like you had a list of matrices and it's going to try to do matrix multiplication together. It gets a little confusing here at that point. So you should refer to the documentation to understand exactly what it's going to do if you try to call matrix multiplication on tensors with more than 3 dimensions or more than 2 dimensions.
Yeah, and thankfully, thankfully you don't usually have to explicitly like multiply these things, and you'll see that in the following slides when we start getting to the actual like neural network parts of it. So you'll usually develop an intuition, I think, for this kind of thing. If you have a good visualization of the way your data is structured, you'll develop a good intuition for when it makes sense for things to be multiplied together and when like, okay, this doesn't make sense. And we'll see like in the future slides, like sometimes like we do something a little weird where like we might reshape something a certain way, or we might squeeze something, and then you guys might be like, well, why do we do that? And like we'll explore that. So we'll have more examples.
Yeah, actually, I believe this next slide is okay. It's sort of a similar example, but this is one example of how like raising it to the power of 2 would be like matrix multiplication, but we don't have to specify because they give us a method for to do that.
Yeah, like x power 2 is like you're squaring the matrix, right? Which is like you're multiplying it by itself, right? So yeah.
Is that clear?
Yeah,
Or
and I
the
also
previous
want
slide is clear. Yeah, go ahead.
Okay, yeah, let's do that. So is this clear? Like, just kind of worry about this case that's shown in the code block, where you kind of have the two entries for the dimensions. It just does standard matrix multiplication. So, like you guys probably learned in math, right? The columns of the first thing have to match the rows of the second thing for the multiplication to be valid, and then the output is going to be the number of rows of the first product and the number of columns of the second product. So that's why we get a 3x5 output, because the first tensor has 3 rows and the second tensor has 5 columns.
All right. If you guys have questions, just make sure you shout it out or let us know in the chat. We'll try to answer it whenever you want. So now we're going into something that's you might not have seen before if you've used NumPy before, which is auto differentiation. This is a really useful feature for machine learning because if you recall back in the back to the neural networks workshop, we talked about backpropagation in detail. We don't have to do all of that by hand because this will handle it all for us. So what you can do is we're taking a new tensor. So this is like the first slide where we're talking about how to initialize a tensor. We're initializing it using a Python list or a nested Python list. So this is a 2x2 matrix of 1, -1, 1, and 1. And we're adding a new parameter here, which is requires grad equals true. So what this tells it is that we want to track the gradient as we're doing operations to this tensor. And in the next one, we're actually doing a few operations. We're raising it to the power of 2, and we're taking the sum of it. And the next one we're doing, this is where we're doing like backpropagation, right? So we've done some operations to this tensor. We're going to backpropagate the gradient, and then we can actually view the gradient of x, which is this tensor. So now we want to see like if you guys can figure out like how did we get these values 2, -2, 2, and 2 from this tensor and these operations. Can you guys kind of either unmute yourself and like try to explain it, or you can try to explain it in chat, however you prefer. You can spend a few minutes thinking about it first. We don't expect an answer immediately.
Yeah, so first do the operation and then see what you get. So first compute like out.
Yeah, it might be easier to like kind of write out what's happening here. In this case, we're treating x like a variable. So you can kind of do that. And power and sum, if you're not familiar with what they do, you can take a look at the documentation, but just to let you know, power will take the tensor and raise it to the power of 2. And then sum will do,
It'll
or
just
yeah,
sum all the elements. So out is just one number.
Yeah, a single scalar.
It's a scalar. So you basically multiply the matrix by itself, and then sum the values of the result, and that'll give you out.
I believe this might be actually element-wise power. Is that correct?
I'm not sure actually. I'll check.
Let's make sure we're. This might not be
I
matrix.
I think that gives you the same output, right? Or no? In this case.
It might be. Let's make sure we're accurate. But if you guys have answers, you can let us know or shout it out whenever you want, whenever you're ready. We'll be waiting.
If how is the linear algebra definition not element-wise, I found that the result of multiplying it by itself was 0, -2, 1, 0, and the sum was -1.
Okay, I believe it is element-wise. That's not right.
Awesome.
Yeah. that sounds wrong. Yeah, thanks for multiplying it out for us though. And I just found the documentation. It is element-wise, power of each element to the exponent here. So it's taking each of these elements and taking it to the power of 2. My bad. Sorry for misleading you guys.
We should have clarified that. Sorry.
All right, in that case, the result matrix is all ones. Sum is 4.
Yeah.
Oh, but how do you arrive at the gradient?
So we got out. So how do we? So what does out dot backward do?
So it might be more intuitive to like treat each of these as a variable, and then see how that how it flows through, taking it to the power and then summing it up. So like let's say this is x1, x2, x3, and x4.
Yeah. So you kind of have to draw out the. I think the best way to do it is you draw out a computation graph. So you have those 4 variables, and then they each result in some value out. And then you want to do back props. You want to calculate the derivatives backwards, how we discussed.
Does anyone want to try it? I'll give it like another minute or so, and then I'll go over the answer.
Paymon, would you describe performing back propagation again?
So the idea, so the idea we discussed in workshop 2 is that the idea is we want to use basically, I guess we didn't really explain it in this way in workshop 2, but really the idea is you want to make use of the chain rule to basically, when you have some derivative with respect to some output value, if you've taken like math 32A, you'll know that basically you can split that up into like its components of multiplying like this derivative. Yeah, so you take the partial derivatives, you multiply them all together through this computation graph, and that will basically give you the output derivative. So the idea is at each step, if you start from the end and then you go towards the beginning, when you compute each partial derivative, if you go all the way back, then you'll have the final partial derivative. When you multiply everything you have together, will be like the partial derivative that you actually cared about. So in this case, like when we're doing like neural networks, like the partial derivatives that we care about is like the derivative of the weight, or the derivative of the cost function with respect to the weights, and the derivative of the cost function with respect to the bias. So basically, if you recall, like in the neural network, like the basically output you get is like the output you get for the cost is like it is dependent on the weights, but it's also dependent on a bunch of other intermediary values. So the idea is you have to expand the derivative that you're trying to solve out into its partial pieces using the chain rule, and then you have to compute each of those pieces backwards. So Kyle says something in the chat.
Yeah, Kyle's actually got the right answer here. So no, I'm not going to show the chat because probably I don't want to make it public. But what Kyle wrote was basically the output is equal to x1, which is this value, squared plus x2 squared plus x3 squared plus x4 squared. So when we're doing x dot grad, what we're kind of asking for is the gradient of x, which is the partial derivatives of x1, the partial derivative of out with respect to x1, partial derivative out with respect to x2, x3, and then x4. And the partials for all of these, because it's just x1 to the power of 2, would be you bring the exponent down, so it's 2 times x1, and 2 times x2, 2 times x3, 2 times x4. So that's kind of the result we had. Since we gave it explicit values here and not variables, we're substituting 1 into 2x1, so that would be 2 times 1. Negative 1 times 2 is negative 2, and then 2 and 1 right there.
Yeah, so you could just you could pretend, like Ben said, that like the 4 entries are x1, x2, x3, x4, because kind of the way we were looking at it before is in workshop 2 was with like variables, right? So it might, I guess it may have been a bit confusing because they weren't variables, but yeah, you could pretend they're just like variables and then compute it like that and then just plug in the values back to get the concrete result. So hopefully that makes sense, because like when you're doing each entry to the power of 2, right? So like some entries squared, the derivative of that is just you pull the 2 down, right? Power rule or whatever. So yeah, so you just basically multiply all the entries by 2 here.
Yeah, and this was a bit of a trivial example because we're only doing like 1 or 2 operations, but you can see how we can keep stacking operations and then maybe like introduce another vector like w equals so and so, and that would be like our weight vector, right? And then, or a weight matrix or tensor, and we can multiply that with x and then do some more operations on it, like apply the activation function, and then we can call backward and then calculate the gradient with respect to x and the gradient with respect to w, and so on and so forth.
Yeah.
So
then,
it will keep track is what we're trying to.
Yeah, so this was kind of a trivial example, like we said, because like it's kind of just like one operation that's being done, but like but the thing is, in neural networks we have like a bunch of different operations that we go through to get to the output, right? So in this case, it's simple, right? You just take the derivative of that function that you applied, but like I said, it's really important when you're actually doing back prop. There's a bunch of operations that we have to go through. So to get that final derivative that we actually care about, the derivative of the cost with respect to the derivative of the weights, you have to kind of expand out that derivative into all of its component pieces and then compute each of those component pieces. And then that is how you get the result. And that's really what this does when you do AutoGrad.
Yep. And now I'll hand it off to Paymon to talk about loading data.
Yeah. Okay. So if that part was a bit confusing, it's okay. Just kind of know that it does the backprop stuff for us, which is really nice. And if you have more questions about backprop, we are happy to talk about that at some other time. But like we already had a workshop on that, so we want to get going with this stuff. So this stuff is yeah. So now we're gonna actually talk about how you load data. Basically, this part's easier to understand. It's just like the syntax of things, what we're actually doing in code. So I'm gonna share my screen again. Yeah, here we go. Okay, so loading data. So yeah, so as we've discussed in depth, right? When you want to train some sort of neural network, right? We're gonna need a data set. So we need to organize that data set in the code somehow, right? And PyTorch has tools to do that for us. So we have to basically define a data set using some certain guidelines and parameters that PyTorch has in place for us. So there's 2 types of data sets just for you to know about. There's map style data sets and there's iterable style data sets. So we're going to look at map style data sets. So it's just good to know that these 2 things exist. Don't really worry about the distinction between them too much right now. So we're going to discuss how you construct a map style data set from scratch. Okay, so basically we need to we're building a class, right? So it's kind of PyTorch is sort of an object-oriented sort of module-like approach to machine learning. And what that means will make a lot more sense as we go through these slides. But basically, we need to define a class that we can pass our data into, our raw data into, to organize it in a way that PyTorch can help us with, right? Because when we want to use all of PyTorch's super powerful like library functions to do like backprop and all these great things, we need to give it data that in a format that it's familiar with and that it understands. So this is kind of how we do that. So in the Torch library, there's a class called torch.utils.data.dataset. So the idea is you need it when you want to create your own custom data set, you need to create a class that inherits from this. So in Python, the syntax and sort of the way you do that is kind of shown here. So yeah, so we inherit from this superclass of this torch.utils.data.dataset. And then our init, so init is the constructor. So I'm just gonna be a bit like talk about this a bit in detail in case like some of you guys aren't super familiar with Python. So init is always the constructor in the class in Python, and you have to you can see before all of these, the first parameter is always self. And like in C++, for example, because I know at UCLA we all have to take C++ classes. So in C++, this parameter is actually passed to the function. It's just done so implicitly. But in Python, you actually have to write this self here. I'm not going to talk about why, because this is not a programming class. But I mean, but you guys should know like self is an instance to the class itself, right? So hopefully you guys know that it's the same way as in C++. And then we pass our construction parameters here. So basically we have two parameters here. So we have statements and truth. So statements are our training examples, and then truth is our labels, right? So yeah. So like statements. So one entry that could be in statement would be like, if we go back to the examples that we were looking at the very beginning of our workshops, statement, one instance in statements could be like a 28 by 28 handwritten digit image. And then truth could be like the label for that image. So like if it's a 9, then it would just be the number 9, right? So we say self.statements equals statements and self.truth equals truth. So this just initializes two member variables to our class, self.statements and self.truth. And we initialize them to the values that we provided in the constructor. This is the same way that most programming languages work. It's just the syntax is a little bit different. Okay, so that was all just kind of Python-y stuff. Now this is the more PyTorchy stuff, right? So when you're defining your custom data set, you have to basically define these two functions manually, get item and length. And you have to define these. So basically, PyTorch will make use of these functions implicitly when it's doing operations, but you have to put them there so when it looks for the function get item, there's something there, right? Because if you don't define that, when PyTorch is doing all of its like operations and it's doing a bunch of nice things for you, it's going to try to call that function at some point to do something. And if you don't have it defined, it's going to be like, well, where's my function? And it's going to throw you a runtime error. So you have to define get item. And what get item does is what the name suggests. So basically, it will return one training example. Okay. So what we define as one training example is one instance of the data with its corresponding label. So in this case, this returns. So if we go back to the example we were talking about earlier, so if we have a handwritten digit and then its label is a 9, so then this would return that for whatever index, it would return that specific index and its label, and it would return it in a tuple. So hopefully you guys are familiar with like what a tuple is, but if you're not, I would just think of it as a list that just has 2 entries in it. That's the simplest way to think about it. So, and that's what it does this automatically. So like for example, in C++, you can't do this, right? You can't return 2 different values from one function. Python totally doesn't care, right? If you do something like this, it will basically return both of these things and pack them as a tuple. Darren, I think they are, yeah. You can look in the PyTorch source code to confirm that, but I'm pretty sure they are abstract classes. Well,
Yeah,
I mean,
speaking. Oh, sorry.
go ahead. Go ahead. No, you go.
No, just like speaking about Python a little bit. Python uses duck typing, so like even if it wasn't abstract, then you would
It
still be able to
doesn't.
do it. Yeah, it doesn't
Yeah,
matter.
it doesn't matter. Python doesn't really. It's not like C++. It doesn't really care. Like I know you guys like when you took 31 and 32. If you've taken those, like you learned all these like super like crazy rules and like all these semantics about like how C++ works. Like those C++ is a very strict language. Python is not as strict as C++ at all. So I wouldn't worry about that. That's not really important. But what is important, so what is statements and what is truth actually? Because we really need to understand the dimensions of what we're passing in here, right? So statements and truth are both lists of objects. So, and we'll see this. So I'm actually going to go to the next slide. So if we define this custom data set using this definition that we have here. So we need to pass in statements and truth, right? So what do we pass for statements and truth here? We pass inputs and labels. So inputs are just statements that we want our network to like predict the outcome of. And the labels are the labels for the corresponding statements. And this works using parallel indexing, right? That's the idea that we're adopting here. So for example, index 0 for inputs is the string bananas are a good source of potassium. And then index 0 is the corresponding label for index 0 in inputs. So bananas are a good source of potassium. The corresponding label for that is true. And then for the thing at index 1, so in inputs, it's apples are usually orange and the corresponding label is false. So basically, this value true corresponds to this first input and this other value false corresponds to the second thing. It's all based on parallel indexing, right? So hopefully you guys see that. So yeah, what we pass in, right, is a list of inputs and a list of labels. And then when we define get item basically packages everything that's at a parallel index with its corresponding label, right? So it will package the training instance that's at index 1 with its label. So you can clearly see that here. So when we print out get item 0, so that's get item for the first index in inputs, it will say bananas are a good source of potassium and it will print its corresponding label of true. Because if we go here, you can see the idea is that it packages the tuple based on the index, right? So if you go to self.statements index 0, that's bananas are a good source of potassium. And then if you go to self.truth and the index is 0, well, that corresponds to true. So then it'll give you a tuple that says bananas are a good source of potassium, comma, true. And like I said, just think of a tuple like a list with 2 elements, okay? And then if you print length, it's just 2 because there's 2 training examples, right? So the first training example is bananas are a good source of potassium, and the second one is apples are orange. So that's really easy to compute. You can just my little thing is covering it. Please go away. Okay. So yeah, it just says return the length of self.truth, right? Because the length of self.true is, and you could have also like just as well returned the length of self.inputs because they're both the same length, right? So that is hopefully pretty simple. You how that works. You just have to define these functions when you're creating a custom data set. So is that clear to everyone? You just have to define those 2 functions that package the data like that. Can I get a yes or no in the chat? Cool. Okay. So yeah, so that's how you create a custom data set. For the rest of this workshop, we're actually not going to care about this too much, which you might be like, well, what the heck? But like, this is mostly useful because when you have a bunch of raw data that you're trying to basically create a neural network to train for, you have to do this. So you might be like, well, yeah, usually you have to do this, which is true. Like usually you do have to do this. But for the remainder of the workshop, we're going to be using pre-packaged data sets that PyTorch gives us. So it kind of already does all that for us. But it's still really important that you understand this, because when you have your, for example, if you guys go on to projects or whatever for ACM AI, like you're gonna have to do stuff like this a lot, because we're not gonna just be using the toy data sets like that PyTorch has, because there's no point, right? There's no point in using the toy data sets. You can't train anything. You can't choose what to train. Then you have to just train based on the data sets that are already there, which is not very useful. Okay, now this creates a data set. Now, there's a distinction between a data set and a data loader in PyTorch, which is very important to understand the distinction of. So when we define a data set, or when we define define a data set, all that does is it creates some class, some instance of, for example, in this case, this custom data set that has this data passed into it, whatever are the data we want. So in this case, it's like this toy example of bananas and apples. So that basically organizes the data into some kind of structure. Now we need to load that data. So what does loading the data do? Why do we need to do it? Okay, well, one, it does something called lazy loading on the data set, which is really useful, because I think the way lazy loading works is it kind of indexes each of the values in your data set in memory, and it keeps track of those indices. Basically, it keeps track of where each entry for each data point is stored in your computer. So then when you need to access the data later, for example, when you're training, it can access the data more quickly. So if you don't do lazy loading, basically it'll be a lot slower, because the program has no idea like where each index is actually stored in memory. So it has to do a lot more work. So if we load it before we do anything, basically it makes everything a lot faster later on. So it does that. That's kind of behind the scenes. And the things that we kind of see more concretely is that it can reorganize our data into batches, which is super useful. And then it can shuffle the data, which is also super useful. So yeah. So let's look at two examples. So let's look at the example where we have batch size 1. So there's a lot of parameters in all of these library functions when you call them. I think there's probably like 20 parameters that you can give this, but we're just going to look at these 3 main ones because these are the important ones. So there's this class here called torch.utils.data.data loader. So you're basically constructing a data loader from this. So you're constructing an instance of the data loader class. And to do that, in the constructor, you pass, so this is basically doing the construction of this class instance, right? So you pass in your fruit data set. So our fruit data set was just this guy here. So we defined the fruit data set by initializing an instance of a custom data set. So you pass in your instance of your custom data set, you pass in what your batch size is, and you pass in whether or not you want to shuffle it. So batch size, and yeah, so hopefully this is intuitive. Like batch size 1 is batch size 1. Shuffling true means you randomly shuffle the data. Shuffle false means you just keep it in the same order that it was in the data set. So let's kind of print out the data loader entries and see what we get. So one other thing that the data loader does is it's an iterable data type. And in Python, working with iterable data types is very important because we can like loop over the entries in the data very easily like this. So fruit data loader is iterable on its own. So you could have done for data in data loader and just printed out the data itself. All this enumerate thing does is that it packages each entry into a tuple where the first entry is an index. So basically it just adds an index to everything just to make it like easier to like view what index you're looking at. Like you can see it here. Like this is index 0, this is index 1. You could have just omitted this enumerate thing and this little value I, and you would have just gotten this. But what's important is that the data loader is iterable. So you can actually iterate over the data using a loop like this. If you just use the fruit if you tried to put fruit data set here, you get a runtime error, because fruit data set is not an iterable object. It's just some class. It's just some instance of some class that doesn't have that property. So you wouldn't be able to loop over the data, which is a problem. Okay, so let's look at what happened here. So for fruit data loader 1 is we just have a batch size of 1, and fruit data loader has a batch size of 2. So let's look at how they're different. So if the batch size is 1, all we do is we didn't really change anything, right? So you just have apples are usually orange, and it's associated with our value of false. And the data loader just casted this to a tensor. You don't really have to worry about that. But it's the same idea that we had before, where you had bananas are a good source of potassium, true, right? It's the same thing here. And then you have the second instance, which is bananas are a good source of potassium, true. So it does it does basically what get item does, right? So when you call this data loader, when you create an instance of it, it'll actually call get item a bunch of times behind the scenes, because that's how it kind of crafts these training examples where each example is corresponding to its label. I hope you can see like it uses get item to do that, because before they're not associated with each other like that, right? Like you just have all the inputs in one array and you have all the labels in another array. So if you want to pack them together, you have to use get item. So this is where I would assume, like, if you didn't implement get item, you would get a runtime error, because it wouldn't be able to repackage the data like this. But yeah, when you have batch size 1, so you just have each example separate, right? So that's just what you'd expect. Now, if you have batch size 2, what do we get here? So now you have a single outer tensor, which represents the batch, right? So each outer tensor represents a batch. So in the above example, the batch size was 1. So there's only one training example in each batch. But in this bottom one, there's 2 training examples in each batch. So yeah, so you can just see both of the training examples are listed in this single batch. So I don't know why this keeps showing up. I don't like that. It keeps blocking my screen. So you have apples are usually orange, and you have bananas are a good source of potassiums, and you have their corresponding label. And you can also see, because we did shuffle true, it's in the opposite order now, right? So before, like, bananas are a good source of potassium was the first one, and apples are usually orange was the second one. But because it shuffled it in the opposite direction. So now it's just shuffled. Okay, so just for a quick recap, and then we'll stop for questions. So first, when you have some sort of raw data, first you need to package it into a data set, in an instance of a data set. And then when you do that, you have to define this custom get item and length parameters. So first you have to package it into that. And then once you package it into this data set, you can then use the data set that you've packaged from your raw data in order to create the data loader. And this data loader is ultimately what we're actually going to be working with. It's what you're going to be looping over when you do your training instances. This is what we're actually using. And that's because this has the lazy loaded data. It's already organized into batches for us, and it performs all the shuffling operations that we might need. And it's iterable, so we can actually loop over it. Okay, so is there any questions about anything regarding data sets and data loaders? It's very important that you guys don't mix up the data set from the data loader, because like when I was first learning PyTorch, like I created like data sets a lot, and then I tried like looping over them. I was like, yo, it's not working. It's because you have to load the data into the data loader to make it iterable and whatnot. So okay, if you have questions, can you ask them? And if you don't, can you just say yes for like you understand what's going on? Or no if you don't, of course. Okay. Yeah. And like the idea is that like you guys are also like running these code blocks. Like I want you guys to like be running all these code blocks, like each slide should be like one code block. And then when you run all of them at the end, when we by the time we get to the end of the workshop, then like you can see like the neural network like training on your own like machine. And I think that will be very satisfying to finally like do that. So hopefully you guys are following along, and like tweak, like I encourage you guys to like tweak like these parameters and see what happens and whatnot. Okay, so we just talked about the whole idea. So of first you need to create the data set, and then you need to create the data loader, right? So yeah, this is the same idea. It's just instead of using like raw data that we defined ourselves, PyTorch has some nice toy data sets that we can use to for learning purposes and whatnot. Just so we can, so we have some standard of comparison and whatnot. So PyTorch has, well, I guess Torch Vision, the Torch Vision library has the MNIST data set inside of it. So the MNIST data set, if you recall, is the handwritten digit data set where each label or where each instance is a 28 by 28 handwritten digit, and then it has all of its corresponding labels as well. So yeah, when you so torchvision.datasets.mnist is a class that's in the Torch, that's part of the Torch Vision library. And then it has the following parameters. So let's just quickly go over what these parameters are. All of this is in the documentation, but we'll of course go over it right now too. So ./data. So what this is saying is put all the, because you have to download the data onto your machine somehow, right? Like otherwise, like you need the data to be stored in your machine somewhere. So this is telling you telling PyTorch what directory to store it. This is saying, do you want the train partition of the data set or do you want the test partition? So by default, it's false. And so it's just a different set of images, I think. So the train data set is like 60,000 images, and then the test data set is like the remaining 10,000. So if you say train equals true, then like it'll give you the training part of it. And then we apply this thing called transform equals torch vision dot transforms dot to tensor. So what this basically does is it just converts the data into tensors. Because if you don't do this, the data will not be organized into tensors. So it will just give you a bunch of errors and nothing will work. So this does like what the name suggests. It transforms all of the data into like a tensor. So then you can index it and do all the cool things with the data sets that we've been talking about. And then download equals true. Like you should just set that to true because you need to download it. So if you said download false, what it would do is it would look in this directory for the data. Instead of downloading it into this directory, it would just look here and be like, okay, here's the data, and then it would just assign this variable to that. If you say download equals true, that's saying like, okay, look, like I don't have the data yet, like give me the data. So it'll do that. And then we do the same thing for the test data set. So this time we don't say train equals true. By default, it'll be false. So if we just don't specify it, it'll be false and it'll give us the test data set. So this is how we get the data set. So this object, like we discussed, has these attributes of get item and length, right? Just like we discussed before. And then now we can use this data set object to construct the data loader. So we'll construct two data loaders, one for the training data, one for the test data. So we pass our train data set. Let's say we want a batch size of 16 and we want to shuffle it. Usually you want to shuffle it. And then we do the same thing for the test data. Okay, so hopefully this isn't too confusing. It's doing exactly the same thing that we've just been discussing for the past little while. It's just that instead of using this manual data, we're just using some data that PyTorch already has for us. So it does the same thing where the data will be organized in the same manner as you kind of see here. So here it would be like, here you would have like all your actual 28 by 28 images, and then it would have the corresponding label for each of them. It's organized in the exact same way. Okay. So this is how you load the data. So that's the end of the data loading phase. So if you guys don't have any questions about that, we can get to actually creating a neural network.
In my Jupyter lab, it said that the Torch Vision doesn't have an attribute data set.
Did you put the S at the end? It's data sets.
Oh.
Okay. Okay, cool. So yeah, and you can actually, we don't have this written in the slides, but what you guys should do if you guys are doing it in the notebook is you should say like for data in train data loader, and then print all of them out so you can see this like this kind of idea except for the MNIST data instead. Like we really encourage you to like make sure you understand that and like just like go ahead and like play around with it. Okay, so actually like we're done loading the data, but let's talk about like quickly how you can visualize data, because that's very important in machine learning. You need to know how to visualize data. So the matplot library is the most commonly used library for visualizing data in like data science in general. So yeah, we already loaded all of our data, so now we can see how we can visualize it. So yeah, so we need to so this, yeah, like I said, so train data loader is an iterable data type. So that means you are allowed to basically cast it to this iterable type. If it wasn't, then like this would not work. So you're basically, yeah, I'm not gonna worry about this. Is like a very pedantic detail. Like just don't worry about that. Just know like if you want to loop over things in Python, the data needs to be an iterable type. So like you need to like cast it to this, so it's like iterable. Okay, so here's here's like our train iterator. Now we want to get one batch, right? So we just like as we discussed previously, like each instance in the data loader is like one batch, right? And you can clearly see that here. Like for each thing, it's one batch. So when we do train iterator.next, it just gets the next instance in the data set. So like right here, it will just give you whatever's at index 0, right? If you type .next, it will just give you whatever's at index 0. And then if you did it again, it would give you the thing at index 1. If you did it again, it would give you the thing at index 2. It's as the name suggests, it gives you the next instance in the data loader. Okay, so if we do .next once, it'll give us the first batch of samples, right? Now the batch of samples is a tuple that contains a bunch of inputs and a bunch of labels, right? We've discussed that previously as well. You can see that here, right? So it's the tuple, so it has all these stupid slide thing keeps getting in the way. So you have all the on the bottom of the screen, so you have a tuple where the first entry in the tuple is like all of the labels for the batch, and then the second entry is like all of the first entry is all the instances in the batch, and the second label in the second index is all the labels in the batch. Okay, so basically what happens when we say inputs comma labels equals batch of samples, it basically splits the tuple. It splits the tuple in half, right? It just like rips off the first index from the second index, and it puts them into two separate variables. Okay, so yeah, you also could have just as well, like instead of doing this, you could just say like batch of samples like index 0, and that would give you inputs, and you could do batch of samples index 1, and it would give you labels. So yeah, so now if we print the size of these two things, we should get something that makes sense, right? So our batch size is 16. So on the outer dimension, we have 16 things, and then what do we have 16 of? We have 16 28 by 28 images, right? That's how the MNIST data is structured. Each instance is a 28 by 28 image, and because we're taking a whole batch of them here, we have 16 of them on the outer dimension. And then for the torch size, it should just be 16 digits, right? Because each of these 28 by 28 images has a single label associated with it, a single digit associated with it. And there's 16 of these 28 by 28 images, so there should be 16 labels, right? So is it clear? So is it clear to you guys why the dimensions of these two things are what you're seeing on the screen right now? Can I get yes or no? Do you guys like get why the dimensions are these values?
What does the 1 refer to?
The one, okay, don't worry about the one. Like the one, the one is just like the one is like PyTorch for whatever reason, like in their because remember we used like one of the things that PyTorch already has, and for some reason they thought it made sense to put a one here. So don't worry too much about that. You can just squeeze it out, right? As we discussed. I think we do squeeze it out at some point. Yeah. Yeah. That's true. Yeah, that's actually a great point. So Trevor says the second value is only one because it's one color channel. Yeah, that's actually why. I didn't think about that. That's correct. So it's a black and white image, so there's only one color channel. Like so technically in this instance you don't need it. It's just that a lot of other data sets we want them to be structured. No, that's actually true. So good point. So like they need all of the data sets to be structured in the same way. So there's like other image data sets. Like next week when we work on the guided project, you guys are going to be working with an image data set that's colored. And then this one will be a 3 instead of a 1. And the reason is just they want to keep like the dimensions, like the template for the dimensionality between their toy data sets like as similar as possible. So here we only have one color channel. So it's just going to be 1. So good catch. I did not think of that. Okay, so now let's talk about yeah, like plotting stuff. So I'm not gonna go into like too much depth of like how you like plot stuff with the matplot library. Maybe some of you guys have worked with it before, but if you just want to plot like something on the screen as an output, you can type plt dot I am image show, so I am show, and then this parameter will basically just this parameter. So let's discuss. Okay, how as an exercise, you guys tell me what the dimensions of this is. This inputs index 0 dot squeeze. Because this is a tensor, right? So what is the dimensions of the tensor?
Uh, 16 by 28 by 28.
Close. It's so inputs is 16 by 1 by 28 by 28. So let's first look. So that's what inputs is. Now let's first look at what happens when we look at inputs, the inputs at index 0. So impact. So there's 16 inputs, right? There's 16 of these images. So if you do inputs at index 0, it just gives you one of the images, right? So that inherently gets rid of this 16 dimension, right? Because we're indexing one. When you every time you index, you go one bucket deeper, right? So now we're one bucket deeper than we were before. So now there's only 1 by 28 by 28. And then we squeeze it so that 1 goes away, and we're left by a single 28 by 28 image. Now, why does this make sense? Well, it makes sense because when we're plotting things, when I have some 28 by 28 image, right, you can clearly see we just plotted it, right? So, and the axes are labeled here. So there's 28 pixels on this x-axis, and there's like 28 pixels on this y-axis. And the matplot library is smart enough to be like, okay, I'm going to look at the numerical values corresponding to each index in this 28 by 28 input 0 dot squeeze tensor, and I'm going to, if the value of it is 0, I'm going to display it as black, and if the value of it's closer to 1, I'm going to display it as white. And CMAP gray just means like you make sure it's a black and white image, so I wouldn't worry about that too much. And then we can also do print labels dot 0. So labels at index 0 corresponds to the label for the first image, right? So inputs 0 is what, like one handwritten digit, and then label 0 is the corresponding label, remember how we talked about how all of this works with parallel indexing, right? So if you print labels.0, it'll say this is a 7, which makes that's what this 7 right here is, right? That's printing labels 0.item. And don't worry about, once again, so what .item does is if you do labels.0, it's going to give you, it's still going to be a tensor, but it's just going to be a tensor with one number in it. So when you do .item, basically whenever you have a tensor that has one item in it and you do .item, it'll just give you that raw value. It'll just like pull the raw value out of the tensor. So it's kind of like squeeze. It's like squeeze, but like when you only have one list left, right? So think of, you have one bucket and then you have one thing in the bucket. But we don't actually care about the bucket. We just care about the thing in the bucket. So when you do .item, you just pull that one thing out of the bucket and now you just have that one thing. Okay. So once again, that's not super important for understanding things. It's just that like, yeah, it's just to make the output like look nicer. Because if I didn't do this, it would say like tensor. It would be like tensor like bracket like 7. So I wouldn't worry too much about that. Okay, so that's kind of how you visualize it. I encourage you guys to play around. If you've written this, play around. If you run this code block more than once, you'll see that you'll get a different image every time. And that's because it saves the state from the previous run. So when you do .next, you were at index 1 the first time, or you at index 0 the first time. So when you do .next again, it'll print the thing at index 2 the second time. And if you do it again, it'll print the thing at index 3. So if you'll notice on your guys' Jupyter notebooks that if you keep pressing run, it'll give you a different image every time. Also, if you do like inputs 1 and labels 1, it'll give you the second digit in the batch instead of the first digit, right? And hopefully that makes sense because there's 16, the batch size is 16. Okay. So now we can actually build our amazing neural network. So this is where the actual fun begins. Darren says, is the iter returning a reference to the iterator of the data loader? I think iterator like just, it's so when you call iter, it's like a wrapper. It's like a wrapper around your iterable data type. So like not all data types are iterable. So sometimes if your data type's not iterable, you can't call this wrapper because, oh, it doesn't. No, don't rerun the entire kernel. Just rerun that one code block. I think it should give you a different one. Like if you restart the whole kernel, it'll give you the same one because it'll go back to. Oh, really? Okay.
Yeah. What my question is like, if you rerun it and it does like iter on train data loader, shouldn't it like return like a
Oh yeah, you're right. Okay. If you had iter in a separate code block and then you did the rest of it, and then it should give you a different one each time. So good
And then
point.
I have iter in the same code block and it is getting a different one. So that means like recalling iter like doesn't give you a new iter function or something. I don't know.
Oh, I see what you're saying. Okay. Yeah, I mean, these are all pedantic details. I wouldn't worry about it. I always thought of iter as just a wrapper around the data type. Like I don't know if it creates a new instance of it every time or what, but it's not too important. So
Right.
yeah, okay. So let's talk about neural networks. Fun. Okay. How do we build a model? So you guys remember how we defined custom data set? Well, we can do that too here, but we do it for custom model, for a custom model. So this is how we define a neural network. So in PyTorch, what you will basically always, almost 100% of the time see is when you define a custom like neural network model or something, you are inheriting from torch.nn.module. So once again, this is like your superclass, and then we're inheriting from it. So this is like a subclass of the NN module class. And the NN module just has a bunch of like super strong tools. Um, like I don't know, off the top of my head, like I know that NN module will automatically like make all the tensors you define inside of custom model like require gradients, and it'll do a bunch of stuff. So it's really important that you always inherit from NN module when you're building a model in PyTorch. Okay, so the idea is the kind of paradigm that PyTorch like adopts is like one of like a bunch of modules and a bunch of like Legos. I like to think of it like Legos kind of. So you define like you basically stick a bunch of modules together in order to make one bigger module, and then that big module is like your neural network. And you'll see what I mean in the next few slides. But for now, just this is how you kind of get started and initialize your network. So once again, we have the constructor here. You always have to call super here. So this is, so I think super like inherits the all of the data members and functionality of the superclass you're inheriting from. So you have to call that explicitly every single time you want to do this. Every single time you want to create your own model, just you always have this little structure that is listed, that is shown on the screen right now. So you always create a class, you always have a constructor, and then you have a, and then you call super, and then you define all your submodules, which we'll get to in your constructor. And then the forward function is defining like how you actually want to feed forward through the network. So this will all make sense. But at the very least, when you create a neural network, you need these two things. Okay. So now we kind of filled it all in. So we're gonna spend a while on this slide, because there's a lot of stuff that just happened. So this is the same, like, so if you guys are following around, like do this in the same code block as this one. It's just, I just replaced all the things that said like define submodules and define feed forward. I just replaced them with like what we're actually going to define it with, right? So yeah, let's talk about what we're actually doing here, right? So in the init stage, you are basically defining all of the submodules, all the pieces that go into your neural network. Okay, so in this case, our pieces are we have kind of two hidden, yeah, so we have one hidden layer, sorry. So this first one is like our input layer. Or no, sorry, two hidden layers. Okay, yeah. So input layer, and then this input layer goes from into some 256 neuron layer, and then this 256 neuron layer goes into 128 neuron layer, and this 128 neuron layer goes into our output. So hopefully you guys can visualize in your head a neural network where you start with so think of the MNIST data set again. What we've seen before, right? So the MNIST data set, the 28 by 28 input. So there's 784 neurons in the input layer. And then that's going to go to a hidden layer that has 256 neurons. And then that's going to go to another hidden layer that has 128 neurons. And then that last hidden layer of 128 neurons is going to go into an output layer that has 10 neurons, which is our output dim. So basically, like the way this works is when you call input dim, so think of it as like the between the two layers, right? So input dim is 784. So you take an input that's 784 and you get an output that's 256. You take an input that's 256, you get an output of 128. You get input of 128, you get an output of 10. In terms of the dimensionality. So these parameters refer to like how many like neurons you want in the hidden layers. Okay. And each of these are like submodules, right? And it's important. I think it's helpful to think of it like this, because like if you think about it, a one layer, if you have one nn.linear, you can, that's technically a neural network, right? Like I could just have one, it's not a very deep neural network, but it's technically a neural network, right? Like I could have one nn linear layer that's like it takes in like 200 inputs, and then it immediately like goes to 10 outputs, right? So then like in that case you have 0 hidden layers, right? Which is like not good. It's not going to do well, but it's still technically a valid model, right? And the reason I want you guys to think of it as like each of these things are technically their own valid model is because like basically like you take all these models and you just like stick them together to create like this one bigger, stronger model. Okay. That's kind of the paradigm that PyTorch likes to adopt of like your big module of your custom model, your neural network that you're defining is made up of basically you can think of it as a bunch of smaller neural networks, right? Like you could imagine like after I create this whole custom model, maybe I want to use this custom model as one small piece in like an even bigger neural network. And then I would just have like, and then I could do like and that big other custom model that I have in my constructor, I would do like self dot layer, and then I would call like custom model, and then I would put the parameters out here. Okay. So the idea is you're basically using a bunch of little building blocks to build your whole big network. Okay. Now that's kind of how, so we defined all the layers in the constructor, and now we need to define how we want to actually perform the feed forward process. Basically, what computation does each training example go through to get to the output, right? So X is going to be a single batch. You can also think of it for the sake of simplicity as like just one training example, but in actuality, X, we're going to pass a whole batch at once. And then we feed forward the whole batch at once in parallel, just because we want to utilize matrix operations and it's faster that way. But you can also just think of it as one training example. So let's say you have one training example, right? You have the one 784 pixels, right? One set of 784 pixels that represents one handwritten digit. So we pass that into forward. And then what do we want to do? We want to pass it through layer 1 first. So our 784 inputs gets, we compute one feed forward cycle to get to the 256 input first hidden layer. So we basically throw all the weights. We compute all the weights. We do all those dot product operations that we talked about in week 2. So that does all of that for you. And then we apply our own choice of activation function here. So this will give you basically the weighted input. So this is like the Z value that we discussed way back in way back in the second workshop. And then we apply our activation function to it. So here we're just using ReLU because ReLU's a good activation function. You could use sigmoid, you could use 10H. They would all probably work pretty well because MNIST is not very hard to train. But we're just using ReLU. And then now you just set X equal to this, right? So you change the value of X. You could also set it to a different value, Y, and then you could set this one to Z and you could set this one to W, but there's no reason to do that because that just wastes more memory because you only need the most recent value at any step. So you can just change the X value at each step of the operation, right? So this is basically the output after this is like the activations like of all of the first hidden layer neurons. So we would have 256 activation values here. And then you throw those 256 activation values into the next hidden layer. So then you get 128 weighted inputs because our next hidden layer has 128 things. And then you apply ReLU again, same idea. And then at the end, now you have 128 activations, and then you pass that through your last layer to get to the output layer. So then now at the end, we're left with X, which is the output layer. So X is going to, at the end of it, is just going to be 10 numbers, right? Because there's 10 neurons in the output layer. So the X at the end is going to be 10 numbers. And then whichever number is the highest, we're just going to say that's out of the 10, we're going to say that corresponding digit is what we classify as. So like it's a 10 digit array, right? So So if index 0 has the highest value, then we classify as a 0. If index 1 has the highest value, we classify as a 1, so on and so forth. You could also apply an activation function here at the end for multi-class classification, like softmax or something that we've discussed in the past. But it's for this toy example, it's really not necessary because you just take the highest value. There's no reason to like transform the data at the end. Is self underscore layer like a variable holding function? It's a class. So self dot layer is a submodule. So it's an instance of a class. So NN linear is so we're constructing an instance of the NN linear class here, right? So you do, yeah. So now this is something, so you might be wondering what this text on the slide means. This is actually really important. Now, like I discussed, all of NN linear itself is like a neural network, right? So it has its own forward function. So when you call self.layer1 and then you pass an x, what you're actually doing is calling the forward function for self.layer1. Okay? So this would be the same thing as saying self.layer1 dot forward parentheses x. Okay, that's what it's doing. The only reason is the thing is you don't usually explicitly call forward in PyTorch, because if you have an instance of a class of a submodule class, so for example self.layer1, and then you just pass it this information, it'll automatically run the forward function. That's what it's saying. So basically in Python, when you pass a parameter into a class instance, it's basically invoking the underscore call function. And because we inherited from NN module, and because all of these things inherit from NN module, when the call function for NN module automatically registers a hook that will call the forward function. So basically, that might be confusing, but all it means is when you call like self.layer1 and then you pass the data, it'll call forward. So this calls the forward function for self.layer1, and then you apply ReLU to the output of that, and then you call the forward function for self.layer2, and then you call the forward function for self.layer3. And then once you did all of that, that was all in the computation for calling forward of our whole custom model. So hopefully you guys are kind of seeing how like all of these things are like their own little mini neural networks. And then when you piece them all together, you can get like some bigger, stronger models. Is that kind of clear to you guys? How we're kind of putting these pieces together? Yes, no, maybe so. Darren says thumbs up. Okay, cool. But this is okay, like this is very important to understand from a programming perspective, so you don't get confused when you're actually coding things. So what we're doing here, so look at my cursor, right? So what we're doing here is we're creating an instance of the nn.linear class from PyTorch, and we're saying that's equal to self.layer1. So self.layer1 is an instance of this linear one linear layer. Okay, it's one instance of it. And then when you pass data directly into that instance of your submodule, it will automatically call forward. Okay, so you can test this on. We haven't actually run the function yet, but when we actually start to run it, you can see like if you were to change this with dot forward, it would give you the same. I'm pretty sure it would give you the same result. But it's just convention, and there's also some other reasons that I'm not going to get into that it's more common to just pass it straight into the call function instead of calling forward explicitly. And you'll see that too when we actually train this custom model. When we pass data to feed forward, we're not actually going to type dot forward. We're just going to pass it straight in like we're doing on this screen. Okay. So how do we train? So we have 10 minutes left. So I think we can get through most of the training part, and then we'll pick this up next week. So how do we train stuff? Okay, so for those of you following around, so now like you should create another code block. So we need 4 things. Okay, we need data. So we already took care of that when we made our data loader. So this is check. An appropriately initialized custom model object. So yeah, we need to create an instance of our custom model, right? So we define custom model. It's this nice class. Now we need to make a custom model object, right? And we call it my model. And if you recall, like the constructor took an input and an output dimension, right? So, and that's exactly the same thing that the NN linear does, right? It takes an input and an output. So just like what NN linear does, we want to pass it an input dimension and an output dimension. So our input dimension is 784 because 28 by 28 is 784, and the output dim is just 10 because there's 10 classes. So yeah, let's create an instance of our custom model and let's call it my model. Okay, so that takes care of that. An appropriately initialized custom model object. Nice. Now we need a loss function and an optimizer. So the loss function, like we said, is the thing that we perform the gradient updates with respect to, right? Because the whole idea, the only thing that the computer or the network actually cares about is getting that cost value as low as possible, right? And this is the whole thing we've just been discussing for the past few weeks, where you need to compute the approximate gradient of this cost function to basically train the model. So we need to define some sort of cost function. So in the past, we used, if you guys remember, we used mean squared error. So that was where we take the output and then we take the labels and we subtract them from each other. And then we square them. So that was the loss function that we were using in our past workshops. So that one's called mean squared error. Here we're just going to use a different cost function called cross entropy loss. But the idea is the same, that we want to minimize the output that the cost function gives. In general, the higher the value of the cost, like the worse our model is doing. That applies no matter what, assuming you're using like a valid cost function, that will always apply, right? So we define our loss function. So we say loss equals nn dot cross entropy loss. Okay. And then we define our optimizer. So our optimizer is like the rule that we want to use to update the network. So the rule that we've been using to update the network in the past is stochastic gradient descent, remember? So after each batch, we get some approximate gradient, and then we update the weights and biases by using that approximate, by moving in the opposite direction of that approximate gradient by some learning rate constant, right? So that's like the update rule that we kind of use. So we need to define something like that. So here, instead of SGD, we use something called Atom. So Atom is the same thing as SGD, or it's an extension on top of SGD that does a bunch of cool stuff that I'm not going to get into the details of. But basically, it does a lot of automatic learning parameter adjustments, and I think Atom uses momentum. Basically, it does a bunch of stuff that will automatically change the learning rate over time, based on like how fast it's converging and stuff like that. But you don't have to worry about that. It's just the idea. We're purposely using things that aren't exactly the same as like the examples we showed in the past, just so it's clear that like there are other options, right? Like for the loss, there's not, mean squared error is not the only option, and for like the optimizer, like stochastic gradient descent isn't the only option. But we define all these things, right? So now we have all these things. That's a nice code block. Okay, now this is the big meaty slide, and the slide that we will probably end off on, because there is so much to talk about in this slide, I think. So yeah, okay. So what do we need to do in each batch? So we have our data loader, right? And we need to iterate over the data in our data loader, right? So each thing in data is a batch. Remember that, okay? Because remember, data loader already discretized our data into batches. So data is just a batch, and we're going to iterate over all of the batches in the data, okay? So what do we first need to do? So just like we did before when we were visualizing the data, we need to split up data into its inputs and its labels, okay? So Yeah. So remember, data is like one batch, and then in each batch, it's like a tuple, and the tuple is the first index of the tuple is like all of the images themselves, and then the second index in the tuple is like all of the corresponding labels based on parallel indexing. Okay, so all we do here is basically rip that tuple apart and put it into two variables. So that's what this does: batch inputs and batch labels. So our batch size was 16. So batch inputs will be that 16 by 1 by 28 by 28 tensor that you guys saw when we were doing the visual. And then batch labels will just be tensor of dimension 16. It's the same dimensions as, do I want to go all the way back? Yeah. It's the same dimensions as this. So 16 by 1 by 28 by 28 and 16, right? So yeah, let's go back there. Okay. So we split it up into those things. And now we need to reshape the data. So this is what I was talking about when I was saying like you'll see like we'll do some weird reshaping later and we need to like discuss why this is the case. Okay. So batch inputs before was a 16 by 1 by 28 by 28 tensor, right? Now, remember how torch reshape works. It takes the first parameter is the input tensor, and then the second is a list describing what we want the new dimensions to be. Okay. Now, our neural network, remember, the first layer is 728 inputs, right? It's just 728 flat inputs in a vector. We've seen the visual of this model many, many times, right? How it's like 784 pixels, and then your first hidden layer, and then your second, and your third, etc. Right? So all this is doing is basically flattening out each of those 28 by 28 images into a flat 784 line. Okay, so it's just basically flattening all the data. So it's in a dimension. The dimension is in a way that like when we pass it into our network, it will not get mad at us. Okay. So is that clear? So there's still 16 different images, right? But for each of those 16 images, we just flatten the 28 by 28 thing into a 784 thing. Is that clear? Yeah. Can I get a yes or no? I got 2 yeses. I feel like that. Okay. Cool. Yeah. So we kind of flattens out our stuff. Okay. And then optimizer dot zero grad. Okay. So what does optimizer dot zero grad do? So, oh, by the way, like these bullet points, each of them corresponds to one line. So this corresponds to the first line. This corresponds to the second line. So yeah. So we described the unpack the tuples, and we described the reshaping, and now we're gonna do what's called clearing the gradient buffer. So the optimizer holds a gradient buffer, which is basically the current value of the gradient that it's storing, and it updates this like cumulatively, right? In a cumulative fashion. So it will keep it'll keep adding the values you're getting at each step on top of each other. But remember, what we want is we want to, after each batch, we want to update the gradients, and then we want like a fresh start, right? Like we need to set it back to 0. So then when we do the next batch, we're building off of like a clean slate again, instead of just like appending or accumulating higher values onto the gradient. If you don't do this step, like you will immediately see that your network's performance will like be very, very bad. Like I think it'll just go to like 10%, which is just like guessing. You need to clear it every time. But it's actually 7:59. So yeah, I'm gonna stop here. We'll start again at this slide because this slide is really important. But yeah, basically the idea, I think you guys can see the idea. Like hopefully you see the pattern. So you do this thing, you clear the buffer, you feed forward. So feeding forward basically gives us our prediction. Now that we have our predictions, we also have our labels, so we can compute the loss by just throwing that into that loss value that loss function that we defined earlier. and then current loss dot backwards will compute the gradient of our loss function, and then optimizer dot step will actually perform all the weight updates. So we're gonna go back to, we're gonna start on this slide again. So I just went over that really quickly just to give you guys a high level idea, but we're gonna break this down more next time. Okay, so it's 8 o'clock. Before you guys leave, please fill out the feedback form. We would appreciate it. And
Let me get a link for it. Or you can go to the slide too.
It's at the end of the slides. So you guys can see on the left side, we're almost done. There's a few slides left. But yeah, it's really important that we take the time to really dissect everything that's going on here. And what's good about the guided project? So yeah, we'll probably finish up in the first hour of next week, and then we'll start the guided project. So what's good for the guided project is so what you guys will be doing for a guided project is you're also going to be doing an image classification task like MNIST. It's just a harder task. It uses a different data set that uses colored images. And instead of 10 numbers, you just have to classify between 10 different objects. So I think one of them is a boat, one of them is a dog. There's stuff like that. It's just 10 random objects and you have to identify them. And you're going to have to use a CNN to do that. And what you'll notice is that it's very you can basically recycle a lot of this code that we're talking about here, and adapt that code to work for the guided project, which is good because you have some sort of framework to work off of, but we'll also just be there and we're just gonna be sitting there answering all your guys' questions the whole time. And I think that's a great way for you guys to really tell us where the gaps in our explanations were and whatnot. So yeah, that'll be next week. There's also gonna be a few little things that will ask you to write from scratch. Just things that are ways you can visualize the data and stuff, just so you guys can force yourself to do that from scratch and get an idea of how to do it. Because if you're just copying the code for the whole thing, it's not as good. So yeah, you definitely won't be able to just copy it, but the idea is you can use all of these ideas that we've discussed to build that CNN. So it shouldn't be too bad, I don't think. So yeah, please fill out the feedback form, guys. Like always, we'll be here until all you guys leave. So you guys have any questions to ask, I think Justin can stop the recording now, and you guys can ask any questions.
Sure. And one more thing to add. So if you're at all interested in these sorts of application-based things, we will have one of our project directors come in and drop in and just talk about how you can get more involved in our projects team. So be on the lookout for that next week.
Yeah. Hopefully, if you guys find this interesting and you want to do it in do this kind of stuff in a much deeper level and a much more from scratch, for a custom sort of task, then definitely please look into projects. I'm sure at least a few of you guys are interested.